Lesson 8.7 is complex numbers. I would pause the video and write down these notes. An imaginary unit is denoted by the letter I, where I squared is equal to -1. So in the past, we've always said that we can't take square root of negative numbers. Now we're defining the square root of -1 to be this letter I. So it's going to be our imaginary component. It's not a real number, but we can still talk about what happens when we do have square root of negative numbers. So if n is a real number, and we're taking the square root of -n, then we can pull that square root of -1 out and call that I, and so you end up with the square root of n times I. All numbers fall under the category of complex numbers. Complex numbers are numbers of the form a plus bi, where a is the real part, or the not imaginary part, and b is the imaginary part. Real numbers just wouldn't have an imaginary part to them. Their b value would be 0. We can look at and evaluate powers of I. So I to the first power is just I, our square root of -1. I squared is -1, that's how we define it, because you end up with the square root of -1 quantity squared, so the square and the square root will cancel. I cubed is -I, because I cubed is the same thing as I squared times I, where I squared is -1 and I is just I. And then I to the fourth is +1. Because I to the fourth is the same thing as I squared quantity squared, or -1 squared, so you get +1. And then you can evaluate higher ones by kind of taking out like what you know. So I to the fifth would be I to the fourth times I, so that'd be 1 times I, which is just I. I to the sixth would be I to the fourth times I squared, so -1, so on and so forth. We can add, subtract, and multiply complex numbers. It's very similar to as if this was an x instead of an I. You just treat it the same way. When you add or subtract complex numbers, you combine like terms, so the real parts together and then the imaginary parts together. When you multiply complex numbers, you distribute or you FOIL like they're two binomials. The only thing you have to be careful of is that if you end up with an I squared, that's the same thing as a -1, so it becomes a real number. So for this first one, I have 3 plus 5i plus -2 plus 3i. So my like terms are the real parts, the 3 minus 2, which is going to give us a 1 in the real part, and then 5i plus 3i, which is going to give us 8i in the complex part. So go ahead and pause the video and try the next one, 6 plus 4i minus 3 plus 6i. So same thing on this one, just make sure you're careful with this negative that it gets distributed to the 3 and the 6i. So you get 6 minus 3 is going to be 3 in the real part, and then 4i minus 6i is going to be -2 in the complex part. Now when we multiply, you would do the exact same thing as if these are x's. Again, the only thing you have to be careful of is that I squared is equal to -1. So I'm going to FOIL this out. 5 times 2 is just 10, 5 times 7i is 35i, 3i times 2 is 6i, 3i times 7i is 21i squared, but I squared is -1, so this really ends up actually being a -21. So then combine like terms, I end up with -11 plus 4i. So go ahead and pause the video and try the last one, 3 plus 4i times 3 minus 4i. So in this one, again, FOILing it out, you end up with 3 times 3 is 9, 3 times -4i is -12i, 4i times +3 is +12i, 4i times -4i is -16i squared, which is -16 times -1, which is +16. So the -12i and the +12i cancel, you end up with 9 plus 16, or 25. So there's no imaginary component on that last part. That last multiplication that we did is something special that we look at, and they're called conjugates. So the way we represent a conjugate is with a bar on top. So z is a very common letter that we use for imaginary numbers. So z bar would be the conjugate of z. So if z is a plus bi, then z bar would be a minus bi. So that last pair that we looked at were conjugates of each other. The outside terms were the same, and then the sign of the imaginary component switched signs. So there's some special things about multiplying by conjugates. What we just did showed that when we multiplied 3 plus 4i times 3 minus 4i, the imaginary part dropped out. And it ends up being a difference of squareds. You have a squared minus b squared, because that factors into a plus b times a minus b. So when you do that with imaginary numbers, the imaginary part drops out, and you're left with just a real number. The conjugate of the conjugate is the original number. If I take two imaginary numbers and I add them together and then take the conjugate, it would be the same thing as just taking the two conjugates of the original and adding them. And then same thing with multiplication. If I multiply two imaginary numbers together and then take the conjugate, it's the same thing as if I take the two conjugates and then multiply them by each other. Conjugate pairs come up a lot. There's something we're going to talk about when we're solving polynomials specifically. Another use for conjugate pairs is when we are dividing imaginary numbers. So we can't have square roots in the denominator. That's not standard form. And since I is technically a square root of a -1, we can't have I in the denominator. So in order to simplify this and write this in standard form, we use conjugates to get this I out of the denominator. So we set up here that when we multiply a number by its conjugate, we end up with just a real number. The imaginary part drops out. So that's what we're going to do. If we want to get rid of this 5 minus 12i, we're going to multiply the denominator by the conjugate of 5 minus 12i. And if we do this to the denominator, to make everything balanced, to just multiply by 1, we're just making 1 useful. Whatever we do to the denominator, we have to do the same thing to the numerator. So in order to put this thing into standard form, we're going to multiply by the conjugate of the denominator in both the numerator and the denominator. So now that we have this, go ahead and pause the video and simplify this, and you should end up with something that doesn't have any imaginary components in the denominator. So foil the numerator and foil the denominator. The numerator, you end up with 5 plus 12i plus 20i plus 48i squared, which is the same thing as minus 48. The denominator, you end up with 25. The two 60i's cancel each other out because one's positive, one's negative, minus 144i squared, which ends up being plus 144. And so you end up with negative 43 plus 32i over 169. Sometimes you'll see right this. A lot of times they'll split it up, so it looks like a plus bi. So negative 43 over 169 plus 32 over 169i. So whenever we want to get a I out of the denominator, we multiply by its conjugate. The complex number system is the number system that involves imaginary numbers. So now we can talk about solving equations that in the past we've said there's no real solutions, and we can talk about their complex numbers. So for this first one, x squared plus 9 equals 0, solve that in the complex number system. So I moved the 9 over and got x squared equals -9, which in the past we would say no real solution. You can never take something and square it and get a negative number. But now we're including imaginary numbers or complex numbers. So I took the square root of both sides. The square root of -9 is the same thing as the square root of -1 times the square root of 9. Well, the square root of -1 is I, and the square root of 9 is plus or minus 3. So we end up with x equals plus or minus 3i. Try this next one. So x squared minus 4x plus 8 equals 0. So it does not factor, so you can either quadratic formula or solve by completing the square. I use the quadratic formula, opposite of b plus or minus b, the square root of b squared minus 4ac all over 2a, where a is 1, b is -4, and c is 8. So you end up with 4 plus or minus the square root of -16 over 2. Again, in the past we'd say no real solutions, but now we know what to do with the square root of -16. The square root of -16 is 4i, because the square root of -1 is I, and the square root of 16 is 4. And then I can simplify this. All of this are even, so I can factor out a 2, and I end up with 2 plus or minus 2i. So imaginary numbers, I is the square root of -1. So now we're talking about complex solutions, something in the form a plus or minus bi, and we don't have to just look at real solutions.